Okay, now what we're going to be doing is applying the first law to control volumes, okay? Instead of looking at just closed systems, we're going to be looking at control volume, and that's where you have mass flow in and out of a system. And for the most part in this class, we're going to be dealing with control volumes from here on out because it tends to be more applicable to most applications, most things. Yeah?
Are most of these examples going to have turbines in them?
Some turbines definitely come into play a lot. You're going to see a lot of turbines in the next month or so or more. Yes, yeah, and some cycles. We're going to be modeling the refrigeration cycle, the power plant cycles, and internal combustion engine cycles. And so all those things, many of those things use the principles of control volume analysis, not closed systems. Now, some of them do still use closed systems, but we also have control. We have to understand control volumes and how to apply and work with them. Okay. And so to analyze control volumes, we have to review a few concepts. Some of this stuff really isn't new. I don't think it's that confusing, but it's very important. That's why we want to make sure we get that clear. First of all is conservation of mass. Now, in a sense, we're going to say mass is conserved pretty much in any of our thermodynamic applications. Is mass always conserved? No. I mean, there's times where we have, like in a nuclear reaction, you may have mass not conserved, or you may have certain situations where mass is not conserved. But for thermodynamic sense, in this class, it really is going to be conserved. And so what you have here is this simple mass balance. You can't make this any easier, and yet this still confuses students. The mass flow into a system minus the mass flow out of the system is equal to the change in mass in the system. Okay? So let's say you had 8 kilograms of mass flowing in, and you had 3 kilograms of mass flowing out. You have 5 net kilograms gained in the system, right? Okay? But I'm going to make it even easier. Okay, I'm going to make it even easier than that. Because in this class, when we talk about control volumes, we're always going to be talking about steady state processes. Okay? A steady state process means that the properties don't change in time. Okay? The properties don't change in time. If the properties changed in time, we would need differential equations to model it. Okay? If the properties change in time, we would need more advanced modeling and solution techniques than what we have right now. And the good news is the steady state assumption works a lot of the time. Okay? Most systems, if you think about them, operate in a steady state. When you're driving your car, most of the time, once you get it warmed up, it's operating in a steady state. Your engine operates in a steady state once it gets warmed up. Your heating air conditioning system in your house, once it gets going, it operates in a steady state. Power plants, they operate in steady state. Most thermodynamic systems spend most of their time operating in steady state. That's what really matters. Okay? Now, we can take advanced courses and do more stuff with this, but steady state's going to follow most everything we need. Okay, what that does here is it makes it even simpler, because that says that the change in mass of the system is 0. Okay, because what that's going to basically say is whatever mass you got flowing in is the same as the mass you got going out. I can't make it any easier, right? That's pretty easy. Okay? So we can write the conservation of mass as the following equation. Okay? You've got the summation of a bunch of mass flows in equals the summation of a bunch of mass flows out. And let me visualize this for you. I think it'll be easier to visualize. Let's say we have some kind of system. And let's say you have 3 mass flows in, M1, M2, M3, right? And let's say you have 2 mass flows out, and these are all M dots, really. They're really dots because they're per time. Mass flow rate is mass per time, right? And let's say you have 2 mass flows out. We'll call it M dot 4, M dot 5. that's saying is that m dot 1 plus m dot 2 plus m dot 3 equals m dot 4 plus m dot 5. It's very logical. It's not trying not to be complicated here. Whatever mass flow you got in is the same as the mass flow going out. You may have a different number of flows going in than you have out. You may have 3 going in and 2 going out. You may have 5 going in and 1 going out. You may have 1 going in and 5 going out. Okay? But the total sum of the masses going in is equal to the sum of the masses going out. That's what that equation says. Okay? I think we can handle that one. That doesn't seem too bad. And yet, that's a really important equation. We're going to use it a lot. Okay? So this leads me to talking about mass flow rate, m dot. Okay? Now, m dot is usually expressed in either kilograms per second or pound mass per second, right? It's a rate of flow of mass. So how many kilograms a second are flowing through the system? Okay? So think of it as flow. Think of it as water flowing through a pipe. Okay? Mass flow rate. And I've shown you this equation before, but I want to remind you of it. The mass flow is equal to the density. Okay, rho again is density, right? Which is equal to 1 over the specific volume. The mass flow rate is equal to the density times the average velocity. I say VAVG. That means average velocity. The average flow velocity.
That was rho times density. Rho is density.
Rho is density. Sorry, yeah, I want to make sure that rho, maybe I'll do triple equal. Rho is density, right? Rho is density, which is the same thing as 1 over specific volume. Rho is defined as density, which is 1 divided by the specific volume. The velocity average is defined as the average flow velocity. I don't know if you know this, but let's say you're looking at a pipe that's going into your house, like your water line. It has an average flow velocity, but that doesn't mean that the water is flowing. If you looked at the inside of the pipe, look at a cross-section of the pipe, not all the water is flowing with the same speed. In fact, some of the water that's on the edges that are kind of touching the pipe flow a lot slower, okay? Because the pipe kind of like grabs hold of it, essentially. The pipe has some friction, and it grabs hold of some of the water, okay? So some of the water on the edges of the pipe that are in the flow field are going the slowest. The center of the pipe is going the fastest. So it actually has a velocity distribution. You don't need to know any of that stuff, but I'm just saying. All you're going to know is that it has a certain velocity, and the only thing else you need to know is this is not volume, okay? That's why I write VAVG there. It's another reason I write AVG is, remember, that's not volume, that's velocity. Mass flow rate is density times velocity times area, right? Cross-sectional area. So the cross-sectional area of the pipe. Okay? This is an important equation for your homework. This is an important equation for future tests and quizzes. Because if you have a mass flow rate, you can relate it to those properties. Density, velocity, and area, cross-sectional area. You can relate it to those things. Okay? Very important that we understand that. And of course you'll have it on your equation sheet, but this is one of those ones you almost memorize because it's just kind of, you use it so much. Okay? All right, another thing to review is remember that for control volumes, this is when you have mass flow in and out, right? This is not a closed system. There's energy term called flow work. I talked about this already. This is essentially the energy it takes to push mass in and out of the control volume. And we can express the flow work as the product of pressure and specific volume. That gives it the units of energy per mass. Okay? So we developed this property called enthalpy, H. We developed this thing called H, and we use it a lot in thermodynamics. In fact, from this day forward, we're almost always going to use H, not U. Okay, we're going to use H because, again, as it's shown here, H is equal to U plus PV, and that PV term is that flow work, okay? The only difference between H and U is the added term PV, which is flow work. Now, practically what that means to you is when you have control volumes, when you have flow going in and out, you use H's instead of U's, okay? In fact, I'll talk to some students at the end of the semester, and I'll ask them about this, and they'll just tell me, well, you know, at some point we stopped using U's and we started using H's, and I didn't know anything else. And then from now on, we use H's, okay? I want you to remember that we use H's to model control volumes because there's actually an extra term of energy that takes to push that stuff into the control volume and push it out. And that's called flow work, okay? So we have that extra term that we have to account for, okay? And so it relates internal energy and flow work, and we call it enthalpy, okay? We're going to use H a ton, okay? You're going to get used to using them all the time now, okay, instead of U's, all right? U's for closed system, H is for control volume open systems. Okay. So now we're ready to express the first law of thermodynamics for control volumes. Okay. There's the first law. This top equation is probably the most general. Okay. This is the most general form. Okay, here's what it's saying. Remember, it's Q minus W. That's what we always write for first law, right? Q minus W. But now this is Q dot minus W dot, okay? Because this is a rate. Dot means per time, right? When you put a dot on it. So it's saying the heat transfer per time minus the work per time is equal to, and then this is the summation of all the stuff going out minus the summation of all the stuff coming in, okay? And you've got to recognize that each one of these here, this is for each outlet. This is for each outlet. And this is for each inlet. Okay? Okay? So each outlet has its own mass flow rate. Each outlet has its own H, its own velocity. That's the V there, okay? That V in there is velocity. Remember, V squared over 2? Hopefully that rings a bell to you, and you go, oh yeah, that's kinetic energy, right? And G times Z, hopefully that rings a bell. Oh yeah, that's potential energy, okay? So each outlet has its own kinetic and potential and its own H, along with its own mass flow. And each inlet stream has its own mass flow, its own H, its own V, its own G, its own Z, own height, okay? It's got it all. Okay? So that's the most general form of the first law of thermodynamics for control volumes that we're going to use in this class. I mean, there's more general you could have, but that's the most general form for this class. Okay? Now, let me simplify this a lot. Okay? We can simplify this. If we have a SISO system, SISO means it's just single input, single output. That means we have one stream coming in and one stream going out. A lot of systems are SISO. Okay? It makes life a lot easier. We have only one stream coming in and one stream going out. If that's the case, you only have one mass flow rate because the mass flow rate going in is the same as the mass flow rate going out. Okay? So you only have one mass flow, and things simplify quite a bit. I have to correct something though on this. That last term there should be a plus G Z2 minus Z1. That was a typo there. For a SISO system, you've got Q dot minus W dot equals M dot, because there's only one mass flow, times H2 minus H1 plus V2 squared minus V1 squared over 2 plus G times Z2 minus Z1. Okay? And recognize those two terms, the V squared terms, that's kinetic energy, right? And the G term times Z, that's potential energy. Okay? Okay? So we can simplify that. All right. Yeah, question?
Looks like that is on the the general form on the inlet, it looks like there's a dot above.
I know. I don't know why that's there. I don't know what happened there. That's a goof. That's a goof there. I don't know why there's a dot on that V. Don't worry about that dot on that V. That shouldn't be there. Yeah. I don't know why that's there. Good observation, but I don't know why there's two dots there that I don't know how that happened. Okay, one more. We can also divide by mass, okay? Remember, when I say Q dot, when I say what's Q dot equal to? Well, it would be something like kilojoules per second, typically, okay? And remember what M dot is. M dot would typically be kilograms per second. So what happens if I take Q dot and divide by M dot? Well, that'd be the same as saying, what's kilojoules per second divided by kilograms per second? Well, if you work that out, the seconds cancel, and you get kilojoules per kilogram, right? So what I'm going to do is divide both sides by m dot. If you do that, here's what you get. You get Q minus W, those are lowercase, equals H2 minus H1 plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. So if you divide out the mass flow rate, then all of a sudden you do not have anything per time anymore. Notice that this last equation I wrote in blue does not have anything per time. And the Q and the W are lowercase because they're per mass. This equation is going to be energy per mass here. So you have three different forms here. I don't think on an equation sheet it would really help you for me to give you three different forms, okay? And this is what gets people confused about thermodynamics sometimes. They say, oh, gee whiz, you got all these different forms of the same first law of thermodynamics. Okay, well, it's because it just depends. I will give you the general form, okay? And then I might give you this bottom one just so you have another form, but I probably wouldn't give you all three. Okay, hopefully you can take the general form and then figure out what form you need in your particular case. Okay, because sometimes you might need the bottom form, sometimes you might need the top form, sometimes you might need the middle one. It depends on the information given in the problem, how you want to reform the same equation. Okay.